Hello, class. I actually haven't done lectures for you for a while because I have been working on the engineering mechanics lectures. But I wanted to get back to you guys, and I'm going to do a couple lectures today, actually. But the first thing that I wanted to do was to do an introduction to like supernodes. And we did the nodal analysis in the last lecture. And I want to look at sort of a special example of nodal analysis. I just want to check something to make sure you guys can see the bottom of this page. I might have to push that up just a little bit. You know, I'm getting to the end of the book. So, I have more books, but I'm getting to the end of the book. And I want to get this supernode out of the way. Will you ever see a supernode? Probably not, if you even had to work it out if you were on a desert island. You know, most of the things that we do nowadays, just like, they still teach students how to add and subtract and do long division. But a lot of students, they're not going to do that much because they'll always have handy access to a calculator, right? The same thing is true with circuit analysis today. You still have to learn how to do circuit analysis. But the chances are, with so many simulation programs freely accessible out there, just about every electrical engineer will have some type of simulation so that they could cross-check and make sure that the analysis that they're doing is, really being done right. I think nowadays you're looking at a sort of, at your level learning. But when you go out and work, you're simulating different circuits that are going to go on printed circuit boards. You are going to be doing that on a computer software, simulation package, more than likely. But you still have to learn why and how that package is doing this. And so what I want to do is I want to, look at an example of how I would use a supernode. And when is a supernode required? Let me draw sort of an example problem that we're going to be looking at that includes both current sources and voltage sources. All right. And that's when you use a supernode, or you could use a super, mesh to solve a problem like this too. But some things lend themselves to super mesh analysis. Some things lend themselves to supernode analysis. You know what I forgot to do? I forgot to turn my thing on. Although I believe that this lecture is going to be one of the shorter lectures, and I've done some very long lectures for you guys lately. So probably a little bit shorter lecture will try to bring this back in line. Where? Timer. Oh, there we go. Okay, so I'm just starting the timer. Like I said, it's going to be much shorter than the 35-minute timer that I put on there. But let's draw the circuit first. You can see I've got a 12-volt voltage source right in the middle. And then I've got these things that are connected down here to a ground. Now I've got two resistors in parallel with those voltage sources that are coming down there. So this is the circuit that I have. Now I'm going to call this 10 ohms. I'll try to write these in here. I don't know if I can get them all, but this would be 2 ohms, and this would be 4 ohms. I think everybody can see what we've got there now. I also want to work with the current sources. This is going to be a 4 amp current source, and this is going to be a 6 amp current source. All right, so that's our the circuit that we're going to look at. We're going to try to find currents that are flowing through those various resistors, as well as finding the voltages at a variety of different points. So let's call this A right here. I'll call this, should have made this a little larger, B right here. I think we know what the voltage is here. V equals 0 volts down at the bottom. And so what we want to do is we want to find out what those two voltages at A and B are going to be. And now I think everybody can see that those voltages are going to be differentiated by 12 volts, right? And this is what we use the Supernode for. Supernode, that's not a Y. Supernode analysis is when we have voltage and current sources both prevalent in the circuit. And you can see here we've got voltage sources and current sources. Now we've got two current sources and we got one voltage source. And I'm using Supernode analysis. So what I want to do is I want to change, let's just make a, you want to get the process down. Okay, so I replace the voltage source with short circuit. Right? So I'm going to replace the voltage source with a short circuit, and that's why, probably drawing it smaller, wasn't all that bad. So let's do that first. So the first thing I want to do is I want to replace, I'm not going to draw it as large. You've got all the values for the individual resistors and stuff in the top circuit, so I'm not going to redraw that entirely. But what I want to do now is I'm going to replace this, right, with a short circuit. See how I did that? I've just replaced that. Not only that, what does that do to that whole row? Right now, all of a sudden, this entire row here becomes one node. Let's call that node A, right? So that all becomes one node now because I've replaced the voltage source with the short circuit. Now I come down through here, I'm still going to keep, right, my current sources in there. I'll draw it a little further down. And I'm still going to keep my, resistors in there. Let me just drop these down so I can find out where my line is going to go. Right? And that is still, just like before, grounded. So all I've done in this transformation from the first circuit that we've got is I've replaced the voltage supply with a short circuit. What that's done is that made that a full node, doesn't it? That whole thing. Now we know that the voltage on this side and the voltage on this side are going to be two different voltages, right? And we know that when we put that back there, they're going to be separated by 12 volts, right? This is going to be 12 volts higher than this. So we know that. And that's from the original here, right? A and B, this is the 12 volts. So we know that the voltage, let's just write down some things that we already know. We know that the voltage at A, right, is going to be equal to the voltage at B plus 12 volts. So that tells us one thing about the voltage differentials across there. Now, that's not for this circuit, though, because in this circuit, we see that the first thing that we're going to do is we're going to make node A contiguous, aren't we? So now, voltage at A and voltage at B underneath this supernode analysis is going to create one node with one voltage. Where would our other node be? Well, I think everybody can see that we've got another node down here, don't we? So we have two nodes. Maybe I shouldn't call that because I've used those places there, A and B. Let's call this node C, because I'm not going to use C for anything. And I'll call this node D. Right? So we've got our two different nodes there. And you're probably saying, well, God, can't we do a summation? That's what I'm doing. Right? So the second thing that we are going to do in looking at this newer circuit where I've replaced the voltage supply with a short circuit, I now can do my nodal analysis of that. Let's do, our nodal analysis for the node that I have at C. So analyze nodes. I'm going to put that down as one section. And then I'm going to say A, right? So I still want to, I'm going to take that away from there. So A, let's do node C. Well, what's going into C? Now we've got 6 amps there. I'll just put this down here so that everybody can see, you know, what we've got flowing in, what we've got flowing out. So let's do that. Now I also, I want to point out something right now. Your book, Alexander and Sadiku book, actually when they're doing analysis, goes 180 degrees against the way that all other books in circuit analysis does mesh analysis. I'm not even sure what their reasoning for that was. But the way that you do it, the way that I always do it when I look at, and we're going to do a loop, you know, we're going to look at a loop here. And so I just want to point out to you that everything that's positive in your book is negative in my analysis and most other people's analysis. And everything that's positive in your book is negative in my analysis. I look at voltage, if I'm going around a loop, and I look at a resistor, I look at it as a voltage drop, right? I don't look at it as a voltage increase. I also look at current that's flowing into a node as a positive. I think your book does that the same way as, but not the mesh analysis, not the voltages. So anyway, let's do a summation, and it doesn't matter if you're you know, plus is minus and minus is plus. It's all going to come out because it all equals 0, right? That's right. So what I want to do with this node, the first thing I see is flowing into the node is 6 amps. So 6 amps is flowing into the node. Hey, those 4 amps are flowing out of that node, aren't they? Does everybody, see that? So I've got 6 amps flowing in. I've got 4 amps flowing out. I have, if I look at all of the currents, let's say that I assume that my current up here is flowing that way. I will call that I3, right? And so it's flowing around here. It's flowing back into here. So it flows out of the node, and it flows back into the node. So actually, I shouldn't put an equals. Why don't we do the full loop? So we're going to sum around that, right? We're going to, or the full node, I should say. So we're summing the currents into the node. And I just want to put this here. Summing the currents into node C equals 0, right? All the currents going in, all the currents going out have to equal. So I've got 6 amps flowing in, 4 amps flowing out. I've got I3 flowing in, right? I have I3 flowing out. I3 flows in here, I3 flows out there, right? How about the other directions? Well, I'm just going to make an assumption. I'm going to make an assumption that the current, I'll call that I2, no, okay, I'll call that I1, and I'll call this I2, right? And I'm going to assume that they're both flowing down. I may be found to be wrong, but I'm going to say, and if I am, they'll come out negative, won't they? So I'm going to say that minus I1 minus I2 equals 0. Can anybody see any other currents that are flowing in or out? I mean, you know, when I look at this node, I see a wire here, so I know a current has to be flowing in or out through that wire. I know another wire here, so a current's either flowing in or out through that wire. I see another wire here. Current's either flowing in or out. Current's either flowing in or out. Current's either flowing in or current's either flowing out. So I have 1, 2, 3, 4, 5, 6. 6 different wires flowing into that node. Have we taken into account all of those? 1, 2, 3, 4, 5, 6. Yes, we have. So we've got the equation that sums up our node. You know, I can simplify this a little bit too, can't I? Because 6 amps minus 4 amps is 2 amps. And then I've got I3, so I've got 2 amps over here, right? Plus I3. Now you might say, hey, I3 is a positive, I3 is a negative. Those things we can just get rid of those. I'm going to in the next step. But I'm going to take these minuses. I'm going to put them over on the other side. So I've got I1 plus I2 plus I3. Now I3 can cancel out on both sides. And what this ends up giving us is that I1 plus I2 equals 2 amps. Right? So there's an equation that we have to honor, and here's another equation that we have to honor, right? So we've got 2 equations. You know what else I've got to do? I'll put B down here because it'll give me a little more room. Another thing that we have to do is we've got to look at node D, right? So this is the summation of the currents into node C equals 0, and this is the summation of the currents into node D equals 0 amps. Sorry. Well, let's look at it. Well, how many do we got there? We've got ground, so we know that the voltage at D down here is going to be ground, right? Don't really need that at all. There's no current, you know, well, there may be current flowing in or out of whatever. But I have my currents here. So my current flowing in or out is going to be 6 amps. Let's do that. So minus 6 amps. You know, I've got 4 amps that are flowing into that, right? And then I also have the current I1 and current I2 that are flowing into that node. So I'm going to say plus I1 plus I2, right? So just a second. Let me check something. Okay, I'm back. You know, sorry about that for a second. Equals 0. And so you can see that I've now got I1 plus I2, and I've got minus 6 plus 4. So this is not an independent equation, is it? This gives us exactly the same relationship between I1 and I2 as we have above, right? But we do have 2 equations here, that equation and this equation. You know, what we can do is we can exchange I1 and I2 because we know that this is going to be 0 volts down here, right? At one end of those is 0 volts. So we can really say that when we're looking at this, I1 is going to be the voltage at A, right? So let's rewrite this. So I'm going to call this 3. Rewrite current equations, right? And let's do that for I1. So we know that VA, where have I seen that before? Well, I've seen it right here. We know that V sub A, right, divided by, what did I say that? 4 ohms, right, because that's I1. And then I2 is going to be V sub B, so plus V sub B over 2 ohms, right, because that's I2. That has to equal 2 amps. I hope I haven't lost anybody. You know, we've got a lot more information here, don't we? Because we know VA equals VB plus 12 volts. So couldn't I write this as VB plus 12 volts over 4 ohms plus VB over 2 ohms, and that all equals 2 amps? You know, when you look at this equation, doesn't everybody see that, you know, I've got VB in both of those. I only have one unknown. So we're back at that beautiful algebra place where we've got one equation with one unknown, and that shouldn't be all that hard to solve. As a matter of fact, why don't we break it up? I'm just going to break it up right now and say that this is VB over 4 ohms plus 12 volts over 4 ohms plus, you know, should we say this is VB over 2 ohms, or should we say it's 2 V sub B over 4 ohms? Haven't we just multiplied the numerator by 2 and the denominator by 2 so that we can get common denominators here now? Right? And that equals 2 amps. So, you know, 2 V sub B plus V sub B gives me 3 V sub B over 4 ohms. And then let's look at this. Let's just rewrite this out. So 3 V sub B over 4 ohms. I don't want to take up too much room. And then, you know, I have 12 volts over 4 ohms. So that's going to give me a current, isn't it? That'll give me plus 3 amps, right? V equals IR. Let's never forget that. V equals IR. P equals VI, right? So you know, that's interesting. Plus this 3 amps here, plus 3 amps, and that 2 amps over there. Can't I bring this to the other side and then have minus 1 amp? Or couldn't I bring the 2 amps over here and then that brings over here? And you know, shouldn't I have a negative in there? Just a second. Let me check something. No, I'm entirely right. I always like to check things, Joe, just in case I had done something wrong, because I just go along here and I don't really look at the work that I've done up to this point. But no, it's exactly right. So 2 amps minus 3 amps is going to give me minus 1 amp, right? In fact, I could put 4 here, just, you know, simplify and rationalize the equations that we already have here, really doing the algebra. And so minus 1 amp is going to be 3 V sub B over 4 ohms, right? 4 times minus 1, amps times ohms gives me volts. So this gives me minus 4 volts equals 3 times V sub B, which says V sub B is going to be minus 1.33 volts. There you go. V sub B, we've used that, and we found out that, you know, it's minus 1.33 volts. Go through my analysis to see how we've done that. And we've done that using this, but we've also used that relationship too, haven't we? And so that tells me that V sub A is going to be minus 1.333 volts plus 12 volts. And that ends up giving me 10.6667 volts, right? And that's V sub A. So we know what V sub A is. We know what V sub B is now. We can easily find out our currents too. So I3, right? When we look at I3 here, we're going through the 10 ohm resistor, and we're going from 10.67 volts to minus 1.33 volts. And of course, that's going to be 12 volts, right? So we've got 12 volts. That's delta V going across that resistor. Delta V is going to be 12 volts. The resistor is 10 ohms, right? So I have 1.2 amps flowing through there, right? Now, let's do the other ones. In fact, that really should have been part of number 6, find currents. I got a little ahead of myself. All right, so we found the 1.2. We can easily now go back and we can find I1, right? So I1, we know is just going to be V sub A, which is 10.67 volts, divided by 4 ohms, right? And I actually have that someplace. Oh, wait, did I call this I1? Yeah, that's 4 ohms. And I1, yeah, 10.67 divided by 4 gives me 2.667 amps equals I1. And then the other one that we want to do is, of course, I2. So I2 is going to be minus 1.33 volts divided by 2 ohms. So that gives me minus 0.67, that's a 7 amps. Right, so I2 is minus 0.67 amps. You see how I've done this in the process? That's the process that you want to look at. You want to look at the nodes, you want to then sum through the nodes, and you can see how this, when I go back to the original circuit that I've got here, I now know everything about that circuit. I know what the current flowing through the 10 ohm resistor or the 4 ohm or the 2 ohm resistor is. I know what my voltages at A and my voltages at B are because I've replaced that and used this as a common node, but I've always kept that analysis between that difference between the two, and I've included that in the analysis that I've done here. So I think everybody can see that supernode analysis gives us the ability to figure out what the currents and voltages are throughout the entire circuit if I have a mixture of current sources and voltage sources. All right. I hope that's pretty clear. Like I say, you're probably, when you get a complicated circuit like this with so much simulation software out there nowadays, you're probably just going to simulate it rather than working through the whole process like I have here. But if you're on a desert island and you don't have simulator software, you'll still be able to do it. Unfortunately, you probably won't have electricity. You never know. I always wondered, why did not Tom Hanks on The Castaway just make an electric generator? No, I'm kidding. But that's what we would do. All right. I'll see you at the next lecture. That's going to be on mesh analysis, and we'll talk about that there. That's a very powerful tool that you'll use, mesh and nodal analysis, but mainly mesh analysis.